All right, so let's talk about specific heat. Specific heat we're going to denote with the letter C. It's the amount of heat required to raise the temperature of 1 gram of a substance 1 degree Celsius or 1 Kelvin. The reason these can be interchanged is because they have the same incremental value. They can be switched around. All right, so when we're talking about heat, we're actually measuring heat and energy. And let's talk about the numbers that we're actually going to be seeing in the units. So we measure energy in calories or joules. So 1 calorie equals 4.184 joules. But this is not the calorie that you see in the back of a food label. That is actually calorie with a capital C. That's actually 1 kilocalorie. And those equal 1,000 calories or 4,184 joules. So understanding what these numbers mean when talking about heat, let's go back to talking about specific heat. And that is measured in joules per gram to degree Celsius. So let's talk about the specific heat of water. Water has a specific heat of 4.184 joules per gram degree Celsius. And what does that mean? That means for every gram of water you have that you want to raise 1 degree Celsius, it requires 4.184 joules of energy. That's actually relatively high compared to the rest of the things on this table and most substances actually. That's because it takes a lot of energy to heat up water. If you think about when you're boiling water on the stove or something, it actually takes a long time and a lot of heat for it to actually raise from liquid, go from the liquid state up to when it reaches the gaseous state. Ice, and specific heat is actually different for each state of matter. So ice, to actually raise the temperature of ice, it only takes 2.03 grams joules of heat to raise 1 gram of substance 1 degree Celsius. And steam is the same way. It only takes 2.01. So it's about half as much energy to raise the temperature of ice or steam versus water. Aluminum is also actually relatively high compared to other metals. Metals have usually typically very low specific heat value, but aluminum is actually pretty high at 0.897 joules per gram degree Celsius. So the lower the number, the easier it is for it to heat up. Okay, so when we use this in actual formulas and to actually talk about the amount of heat needed or how much temperature is shifted or how much mass we need of a certain substance. And so we're going to use this formula, Q equals MC delta T, or Q equals MCAT. Q is, when we're talking about heat, is a symbol for heat, and that is usually measured in joules. It could be measured in kilojoules or calories, it doesn't make a difference. But Q represents the amount of heat needed or heat required or energy. M is our symbol for mass. It's usually measured in grams. C is our specific heat of that particular substance, and delta T is the change in temperature. It can be, again, it can be in either Kelvin or degree Celsius. It doesn't make a difference because it's the change in heat. Now let's talk about how this affects a phase change diagram. Okay, so this is a phase change diagram for water. Let me write that down. Okay, so notice if you look at the slopes for the change in energy as we increase the temperature of a solid versus liquid, notice solid has a steeper slope than liquid. That's because liquid requires more energy to increase the temperature per gram than it does a solid or gas. These are actually steeper in slopes than it is for a liquid. So this actually affects the phase change diagram as well, and that's because of specific heat. Let's go over and solve a problem together and figure out how this actually affects other things. So we have an architect, and he's actually really interested in sustainable energy. So an architect designs a house that is partially heated by solar energy. Heat from the sun will be stored in a solar pond, similar to that of a swimming pool. So we have this pond that we're dealing with. It's made up of 14,500 kilograms of granite rock, and then inside that it contains 22,500 kilograms of water. All right, together the granite and the water absorb heat during the day and release it at night, which then releases at night into the house, heating the house at night. The architect found that the solar pond increases 22 degrees Celsius during the day and lowers at 22 degrees Celsius at night. So how much energy does it release and absorb during the day? So let's underline the information that we have. Let's start with water. Since we have two substances, granite and water, the amount of energy it actually requires, the total amount of energy is going to be the Q of water, a granite, plus the Q of H2O. So let's the Q we know equals MC delta T. Okay, so let's first deal with water. Okay. Well, water, we have the mass is 22,500 kilograms, and we want it in grams. So we're going to make it 2.25 times 10 to the 7th grams. Okay. The C of water, or the specific heat of water, is 4.184 joules per gram degree Celsius. Now, the reason I wanted this even in grams and I couldn't use kilograms is because my unit for specific heat had grams in it. So I want to make sure these units are the same. Okay. So then we know that it changes the temperature. It increases and decreases in temperature 22 degrees Celsius. So our change in temperature is 22 degrees Celsius. Okay, so when I multiply these all together, I get the amount of energy that's required, or that is absorbed by this solar pond, or at least the water within the solar pond. And so I multiply these together, and we get 2.1 times 10 to the ninth joules. And the reason I got joules is because, again, specific heat is measured in joules, or this specific heat is measured in joules. Okay, let's talk about the Q for granite, because the pool is made up of water and granite. The mass of the water is the mass of the granite is 14,500 kilograms, which is 1.45 times 10 to the 7th grams. The Q for granite, if we look at our table, is 0.803. And again, that's changing 22 degrees Celsius. And I'm just not putting the units in just because I want to save some space. All right, when I multiply these all together, I get 2.4. Sorry, that's not true. I'm sorry about that. I get 2.6 times 10 to the 8th joules. Okay, so the total amount of energy that this actual solar pool gains and loses in a day is 2.4. When I add these up, 2.4 times 10 to the 9th joules of energy. So this actually saves us a lot of energy when we're actually going to heat up or cool down our house. So we're saving a lot of money in sustainable energy by using the solar pool. So specific heat actually tells us a lot of different things, and it's unique for each specific substance, and it's the amount of energy required to raise 1 gram of a substance 1 degree Celsius.
This is the last section in Chapter 9, and we're going to look at energy needed for a phase change. So you remember this diagram, and this shows you the energy, which is along the horizontal, that's required for a solid to change to a liquid to a gas. So we'll usually refer to water, but every substance undergoes these phase changes. Now the heat of fusion of water you defined the other day, and the heat of fusion in particular for water is 334 joules per 1 gram of water. So you might remember when we were studying this in Chapter 9 that a joule is an energy unit, and you need that much energy to melt 1 gram of water or to change 1 gram of liquid water to solid water. That energy would be released. So the heat of fusion of water is 334 joules per 1 gram of H2O. The same amount of energy is released when 1 gram of water changes from a liquid to a solid. So this is absorbed when a solid changes to a liquid. So I'll say absorbed when solid to liquid phase change occurs. And then I say the same amount of energy is released when 1 gram of water changes from a liquid to a solid. So this absorbs the energy, and we use a negative sign to show the energy released. That heat of fusion is occurring right here. So if it's melting, it's adding that 334 joules per gram of water, and if it's freezing, it's releasing 334 joules per gram of water. So if you think about making ice cubes, you put in liquid water in your freezer. The water's actually going to give out some heat energy, and your freezer's going to remove that from the actual freezer. Now, heat of vaporization. It's the amount of heat required to change a unit mass of a liquid to a gas without an increase in temperature. So heat of vaporization of water, if we talk about water in particular, look at the value of it, 2,257 joules per gram of water. This is absorbed when liquid water changes to a gas, and it's released when that water condenses from its vapor. So this, when it's released, it's releasing 2,257 joules per gram. Think of this when clouds form. This is a lot of energy per gram of water, and this is really the energy that drives storms. Because you have warmer air, it can hold more water, and so you have a lot of water vapor in the air. So our last slide is just to remind you of this cycle from a gas to a liquid to a solid. Remember your terms: condensation to freezing. If we add energy, we go from melting to evaporation. And then remember your terms, going straight from a solid to a gas and a gas to a solid. Notice your red is when heat is given out or released, and the blue is when heat is absorbed.